Now, in this question, we want to calculate the molar heat of fusion of a substance in kilojoules per mole if we have 300 grams of this unknown substance with a molar mass of 180 grams per mole, and we also know that it's going to give off 65 kilojoules of energy as it freezes. Now, to understand how to do this question, you need to know the phase transitions between a solid and a liquid. And so if we have a solid here and a liquid here, and it goes through a phase transition where we go from a solid like this to a liquid over here, that's going to be melting. And so we're going to have a delta H value that's going to be associated with this phase transition. And that delta H value is going to have to be a positive number. And that's because this delta H right here, this is going to describe how much energy is going to be required to break the intermolecular bonds of the solid to go to the liquid over here. Now this does not break the covalent bonds, it's just going to break the intermolecular bonds, which could be something like a hydrogen bond or a dipole-dipole bond, but energy is going to be put in to go this way. Now if we go the other way like this, if we go from a liquid to a solid, well, that's going to be freezing. And so we're going to have a freezing phase transition if we go in this direction. And that delta H value is going to be the same but opposite in sign. And so this is going to be a negative value. And so this right here, this delta H, describes the intermolecular bonds that are going to be forming from a liquid to a solid. Now this right here, this gives off 65 kilojoules of energy. There's an equation that's going to relate the amount of energy given off to this delta H value. And that equation is going to look like this. We're going to have Q, and that's going to be equal to delta H times N, like this. And so this is going to be the energy that's going to either be released or required. And in this case, it's going to be given off, so it's going to be negative. And so it's going to be released, which means this is going to be the freezing right here. And so what I'm going to do is I'm going to say that we have this negative 65 for the energy that's going to be given off, and that's going to be equal to this delta H value here. And so I'm going to put a delta H here, and then I'm going to multiply that by the number of moles that I have of this. Now to get the number of moles, what I'm going to do is I'm going to say that the number of moles is going to be equal to the mass in grams divided by the molar mass. And the mass in grams is 300, so I'm going to do 300 here. And then I'm going to divide that by the molar mass of 180. And so when I do 300 over 180 like this, I'm going to get 1.66. And so this is going to be the number of moles that I have of this unknown chemical right in here. And so what I'm going to do is say that I have 1.66 like this. Now when I solve this right here for delta H, I'm going to get that the delta H value is going to be equal to negative 39, and that's going to be in units of kilojoules per mole. And so now that I know that I have this right here in kilojoules per mole, I'm going to take this value here and put it in here like this. And so that's going to be the delta H. It's going to be equal to, now this is going to be a negative 39. And we know that this number here is going to be the same as this one, just opposite in value. And so what I'm going to do is I'm just going to say that this right here is going to be the delta H for the melting is going to require plus 39 kilojoules per mole. And so the answer to this question is going to be positive 39 kilojoules per mole.